صباح الخير عليكم. السلام عليكم ورحمة الله تعالى وبركاته. I am humbled by all these nice words about me. Thank you very much for the introduction and also to the organizing committee for having me. I must say that coming from Singapore, which is about 18 hours flight to Morocco, it's a big decision to come. But I think this is an event you don't want to miss. It's very important. We had nice introductions here about Moroccan programs on solar and wind energy. It's fantastic. And I think I agree with all the comments that have been done that as a scientist and the researchers, Moroccan or non-Moroccans, we have to contribute to this huge effort. Morocco is at the intersection of, I would say, three cultures. One is the Middle East. We are Muslim, we are Arab. So we have this Middle East culture. Spain is only 10 kilometers or 15 kilometers to Morocco. So we are also having this influence from the north, from Europe. And Morocco has a very, very good strategic, geographical, but also economical position with Europe. There are many trade agreements with the Europe that allows actually Moroccan product to be exported to West Europe with less taxes. But also we are Africans, all right? So our route here, it starts in the desert, Sahara. It's not very far from here. So you can feel the heat of Africa. So we are proud actually to be at this intersection of these three big civilizations or whatever cultures. And Morocco is the melting point of all of this, which means that it can play this role of transmitting, you know, the know-how and the experience to both Middle East and Africa. And personally, I see the future of Morocco with Africa as great. So what happens in Morocco today in this sustainable energy and programs, I think will impact what will be the future of energy in Africa. So anyway, I'm very, very happy to be with you today. And this year was absolutely an incredible year. I can tell you about a year ago, in November 2013, I was in the middle of a meeting with the patent office committee, and then my cell phone rings because I have a lithium-ion battery in it, of course. And then I had this gentleman calling me from Washington, D.C. He's the director or the president of the National Academy of Engineering in Washington, D.C. He said, I'm talking to Prof. Rachid Yazami. I said, yes, sir. He said, well, I have some good news for you, and you have been nominated for this Draper Prize. I said, what is the Draper Prize? I didn't know at all. He said, well, you know, let me tell you a few words. And then little by little, he explained what is the Draper Prize, and it was awarded actually to the inventors of GPS and all the, big satellites and space and avionics and all engineering. And I felt really very humbled. I'm like, wow, this is really exciting. And then he explained me that actually it's a team work. And we were actually 4 laureates to receive the prize. And because of this, I would like just as introduction to give this credit to my colleagues who also contributed a huge amount of their invention and taking some risk back to the 80s. All right, it's like more than 40 years ago. And I would like to start by showing you this picture, which has been taken on the 18th of February this year at the Academy of Science in Washington, D.C., with the laureate of the Draper Prize here. I will show you a better picture, and this gentleman is the head of the National Academy of Engineering. So the Draper Foundation is located in Boston, and it was founded by Mr. Draper. And he's actually the equivalent of the Mr. Nobel in Sweden. And because in America, engineering is so, I mean, not only in America, but mostly in America, engineering is so important that they said why the Nobel Prize Committee did not have a recognition to engineers. They are giving it to chemists, physicists, economists, and peace, and etc., and biology and medicine, but not engineering. So they said, okay, we decided that to create this equivalence of the Nobel Prize. It's not the Nobel Prize, it's the Draper Prize, but it's the equivalence of Nobel Prize for engineers to honor the people who contributed to improving life of humanity and finding solutions. And I remember this very important speech by the head of the Draper Foundation. He said, we are not recognizing genius people. What we recognize is people who contribute to make things work. That's it. If your idea is not genius, but it's working, we give you the Draper Prize. So it's unlike the Nobel Prize, which sometimes recognize theories of very small particles in physics whatsoever. This is different. So it's really for things that work and prove to actually contribute to help humanity in some aspects. Okay, so this is maybe a larger picture. So let me introduce you our senior researcher, Professor John Godinoff. He is now 92 years old. But if you go to University of Texas in Austin at 7 a.m., you will find him in his office. And he's still working very hard. At 7 p.m., he leaves and has a wonderful group of at least 30 people working with him, 92 years old. Incredible. I admire him very much. I respect him very much. And I think he really deserved this recognition. And I can tell you he was happy like a child when he got this recognition. This gentleman is Dr. Yoshino from Asahi Chemicals. But briefly, let me tell you, back to John. John and me, almost the same year, completely independently, 1979, 1980, we discovered completely independently, for John, the plus pole, the cathode of the battery, and for myself, the anode, the minus pole. And it was early 80s, and many people actually were working at that time on how to make primary lithium batteries rechargeable. Primary lithium batteries is non-rechargeable, and they were already commercialized in Japan in the 70s, mostly by Sanyo and Panasonic. And they provide a much higher energy density than any battery at that time. But they were not rechargeable. And there was, in the late 70s, early 80s, a tremendous effort to produce or to develop the rechargeable version of lithium-ion batteries. It was really, really, really challenging. Just to tell you one thing, how difficult it is and how unlikely to develop a new battery. If you have a battery that you want to last for, say, 3 years, and you expect to have something between 500 to 1,000 cycles. If after 1,000 cycles, your energy density has decreased by 20%, for instance, that's mostly what we expect. You have, at each cycle, to reach an efficiency of charge and discharge of at least 4 nines, 99% efficiency. Nothing in nature gives you 99%. It's almost impossible. But still, for some reasons, I mean, the cathode of John and the anode that I invented provide this. And it was, for me, an incredible development when first time I met this gentleman, who is Dr. Nishi from Sony. They invited me in 1990 to their corporate research center in Yokohama in Japan, and he convinced me I was the first ever, Japanese or non-Japanese whatsoever, to learn that Sony was going to launch in a couple of months the first rechargeable lithium batteries. And I said, why did you invite me? He said, you know what? We are using your anode. Now you have to know it. in myself, I couldn't imagine that this anode could reach that level of, popularity and efficiency and so on. So anyway, there's the four players. Dr. Yoshino, in 1985, 86, like 6 years after the invention of the anode and the cathode, produced the first working prototype. And he did something revolutionary. Let me tell you, things can be very simple for us now, but in 1985, it was not that obvious. I would say that the great majority of people working on rechargeable batteries, when you have a rechargeable battery, you have to ask yourself, when I make this battery, would it be in the charge or the discharge state? You are going to make 1,000 cycles, charge and discharge. So when you make it, is it discharge or charge? In the 80s, everybody thought it should be charged, except this gentleman. This gentleman said, no, I can make it in the discharge state and start by charging it. It looks very simple, but it's fundamental. It changed the world. Just very small idea like this changed completely the world. So Dr. Nishi was the first, and his team, to provide the first prototype. And then he explained me why, Asahi Chemical, who is one of the leader chemical company in the world, why Asahi Chemical did not decide actually to produce themselves the lithium-ion battery. They said it's the way how business is made in Japan. They put companies according to their products, and if you are in a chemistry or, say, pharmaceutical or something, you don't produce batteries, otherwise you have problems, okay? So what they did, they went to battery producers like Sony at that time, or Panasonic and the others, Sanyo, and they said, hey, we have this prototype, do you want a license? And the first who took the license are Sony. Okay, now this is another very important step. You have a prototype. We are in around 1987, 89, okay? In 1989, there was another company in Canada called Moly Energy, and they announced very loudly, we have the first lithium rechargeable battery. Fantastic, it was in news. I knew the head of the R&D there, a good friend of mine from Germany, and he came to me in Grenoble and he said, Rachid, we have really a rechargeable battery, it's working, etc. I said, fantastic, it's congratulations. Unfortunately for them, when they started the production, 6 months or less than a year after, one battery had the bad idea to heat up in a cell phone, and the Japanese gentleman were not burned, I would say, he just had his ear a little bit hot, nothing. No explosion, no fire, nothing. But this event, this incident, they stopped everything. They said, this battery is not safe. And the company in the Moly Energy disappeared, totally. All right. So now we are in 1990, 2 years later, and Sony, the giant electronics company, decided to take the risk to totally, have the company collapse and introduced the rechargeable battery in 1991. And when I discussed with Nishi, I said, you are like a pilot in an injectable seat, If one of your million batteries has bad idea to catch fire, Sony is done, finished. But fortunately, it didn't happen. And then the batteries now, in 2013, there were more than 14 billion, more than almost the double of humanity population, batteries produced worldwide to generate a market of about, now it's close also to $15 billion. It's a huge market. So it's a success, it's a wonderful story, and I'm really very proud to be part of it, and this recognition, as you can imagine, has completely changed my life. His Majesty the King Mohammed VI, welcomed me in the 30th of July this year during the Trône fête, la fête du trône, and gave me this medal of intellectual competency, which is the highest level that can be given to any scholar worldwide. And I was really humbled and proud to be at that level of honor. Now, the thing is that, as probably you mentioned, I'm kind of international scientist. I love science, but I love also cultures, and I love to travel. So when I was invited to Sony Center, I was spending 2 years sabbatical in Kyoto. So I learned a little bit of Japanese, and I learned a little bit of the Japanese culture. And until now, when I go to Japan, I can feel this welcome, and people know I can understand Japanese. They are careful when they speak Japanese. Yeah. Himitsu desu, huh? So anyway, and then I come back in 1990 to Grenoble, and in 2000 I moved to California, and that was actually to be part of the NASA effort to launch this robot on planet Mars. Spirit and Opportunity. The early 2000s, they were launched, and now, so I was a little bit involved to test batteries and do the prediction of life of batteries in the Mars surface of Mars conditions. In Mars, temperature goes from -100 to +100. It's not like in Earth. So -100 degrees C, not so many batteries can stand. They just die. And +100 degrees C, it's almost dead. So conditions are very special. And according to the calculations of my colleagues in NASA, they said this robot will last 3 months. And after 3 months, the batteries will be dead. Some of them are still working now, 10 years later. All right? So these batteries last forever. I mean, almost last forever. It was a very good surprise. And at least one of the robots is still sending information daily and so on. So anyway, and at the same time, there was this effort by the US Department of Energy to develop next generation lithium-ion batteries, and I worked with some of my colleagues at Caltech, and it was also another wonderful experience to be part of the Caltech community. Probably you heard about Caltech. This is 3,000 people, including everybody, university, one of the smallest in the US. But they have 32 plus Nobel Prize laureates. To get a job in Caltech, you have to be potentially 80% chance they will get Nobel Prize. Otherwise, they will not take you. So that's one of the rules, okay? So they are very, very, very selective, but I wasn't part of I would say, the tenured staff. I was just a visiting professor. I qualify myself as just a tourist coming there and taking pictures. But I was part of this community, and it was absolutely an unforgettable experience. Anyway, and then 10 years later, I mean, in 2007, I started the company in California, and that was about a new chemistry that we developed where we wanted to replace lithium with fluorine. So this was the first anionic and not cationic battery. And then I moved in 2010 to Singapore, where now I live. And in 2011, I started another company, which I will introduce you a little bit. This company called KVI. It's a Kelvin Volta innovation, and you see here, if you can read, is the battery intelligence company. We want to make batteries smart, so I will explain how batteries can become smart. Okay. All right, so this is the outline of my talk. I guess in the audience, maybe not the majority of people are not very familiar with batteries. So I thought it's maybe a good idea, at least for those who never had like the chance to have like a short explanation about how a lithium-ion battery works. I would like just to introduce this for you, to explain what is the anode, the cathode, and the electrolyte. And I will cover, the energy, power, and life performance of batteries, etc., and then go to the intelligent battery and the thermodynamics technology that we developed in Singapore and in California. All right, so very simple. Well, I mean, at least in principle, the lithium-ion battery is quite simple system. You have 2 electrodes, and this electrode will store lithium inside. So they will intercalate or alloy somehow with lithium. And during this process, one electrode is either generated or used. So this is a process called electrochemical process. It can be a reduction or an oxidation reaction, all right? So every time you have a lithium that is moving from the minus to the plus, you have an electron that is circulating in the outside. So this is how you power your cell phone, laptop computer, electric car, whatsoever. This is very simple. So you have the anode here, the cathode here, the red dots here are lithium ions. And between the anode and the cathode, the minus and the plus, you have a separator, because you don't want to have an electric contact between the anode and the cathode. Otherwise, electrons will flow inside the battery, not outside. All right? So you have to have this electronically isolating material. And this electronically isolating material is wet with a liquid electrolyte. And electrolyte, by definition, is a medium where ions only move, no electrons. All right? So here you need to have a lithium conductive material that allows lithium, once it is produced on the anode during discharge, to flow from anode to cathode. And at the same time, electrons will flow. So I have an animation here just to show you during the charge of the battery. I'm taking the ions from the cathode, putting them in the anode, and at the same time, electrons are flowing. This is what the charger basically does, all right? Just take electrons from the cathode and put them in the anode. And of course, the opposite mechanism happened during the discharge. So now, electron will flow from, all right, the electron will flow from the anode to the cathode, and ions will go from the anode to the cathode at the same time. So as you have the electrical neutrality of the whole system, and this operation can be repeated many hundreds of times, maybe even thousands of times. And my colleague here from the solar energy laboratory in Germany will show you later their battery that's performed more than 10,000 cycles. So this battery can be really absolutely outstanding. So this operation can repeat itself, and you know, the system is working nicely, as long as, again, there is no break-in in this separator, there is no direct contact here, and also lithium ion, when they are exchanged between the anode and the cathode, go to the right side in the electrode. If they make mistakes, and mistake can happen, then you are losing your capacity. Okay, so briefly, I would like to introduce you some of the major anode materials that have been, you know, introduced or used in commercial batteries. So far, fortunately, so somehow, graphite, the one invented in 1980, is still the preferred anode material. It has this hexagonal structure here, lamellar structure. Very simple material. It has only one atom, carbon. The carbon atoms in the layer make hexagons, and there is a stacking of the hexagons along the C-axis here. AB, 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 or ABC, ABC stacking. And during the process of lithium intercalation, these layers will glide, so as you have AAA stacking, and so on. So it's a very well-known system. It's a very highly reversible, because when you put lithium into the graphite, the carbon-carbon bond, which is very, very strong, never breaks. This binding energy between carbon atoms is stronger than in diamond. Stronger than in diamond, so it's almost unbreakable. All right, the other prospective anodes are the lithium titanate. This formula, here the amount of capacity per gram is about 200, and they have the spinel structure, and others like silicon, very high capacity, but there are some few issues with I would say efficiency and also life of this anode. But anyway, These are only the major, and of course, people are very, very creative to modify this anodes here by doing some substitution or modification on the surface and so on so as to improve the performance. So, but still today, if you buy a battery, the most likely chance that you find either graphite, maybe 95%, and lithium titanate 5% as the anode is. This is what you find now in a lithium-ion battery. The cathodes, so the historical cathode that was developed by John Godinoff, lithium cobalt oxide, it has an hexagonal structure where actually lithium is intercalated between two slabs of cobalt oxide here. And basically what the slide do, they glide and then they expand or contract according to the amount of lithium between the layers. And this process can be repeated many times because the COO2 slab is very, very stable. You cannot remove lithium from, or oxygen, excuse me, from the, although it's thermodynamically favored, but you cannot make lithium oxide, for instance. So this slab is very, very strong. So that's why this reaction can be repeated many hundreds of times. There is another family of materials called the spinel cathode materials, especially the one of the, I would say the number one example of this family is lithium manganese spinel, Li-Mn2O4. It has this spinel cubic structure. And you have the lithium iron phosphate. And when you hear phosphate in Morocco, that means something, okay? Because we have the OCP, which is the number one exporting company in the world for phosphate, and the lithium iron phosphate and other of the same family has the orthorhombic phase structure or symmetry, and it can intercalate lithium into channels. So these materials correspond to absolutely almost 99% of the materials that are used in commercial lithium-ion batteries. But there are some variation because lithium cobalt oxide, people consider that cobalt is too expensive, so we have to replace it or to substitute it with less expensive materials like nickel, manganese, etc. So now we are talking about NMC materials, but they have almost the same structure, basically the same, except the slab has in addition to cobalt, it has nickel and manganese. Same thing for the lithium manganese spinel. You can substitute parts of the manganese with nickel, and you can have also very high voltage cathode materials that are based on the nickel manganese spinel. And lithium iron phosphate the same. The transition metal here, iron, can be replaced by other elements, including manganese and cobalt and nickel and so on. So all of this is actually to improve the performance of the system. There's huge amounts of work on, providing the new materials with the new improved characteristics. So this slide shows actually in this scale of capacity, which is how much Coulomb or milliampere hours you can store per gram, and the voltage at which the system will work. So for an anode, the voltage should be low, and for cathode, the voltage should be high, all right? So ideally, a battery that has graphite as the anode and this material, which is the nickel manganese spinel, will provide you 4.5 volt, right? So that's very high. So voltage is very important in the energy, of course. It's a part of the energy density, times the capacity. So if you multiply the capacity by the voltage, that gives you the energy density. So you see here that the titanium, titanite, and titanium oxide is around 1.2, 1.3 volt. And there are many other materials based on other oxide, cobalt, iron, and tin, sulfide, etc. that provide also high capacity, but the voltage is high. And now the prospective anode materials are here, the carbon nanotubes mixed with silicon and silicon as well, and we are in this area. So anyway, there are huge amounts of work to develop, to come with a new anode and new cathode formulation to improve energy or power density of the batteries. All right, why lithium-ion batteries are so popular? Number one is their energy. They can store per kilo or per volume. So this diagram shows you the energy density per weight. So when you take 1 kilo of a battery, the full battery, how much energy you can get. And this is the energy density per volume. So for some applications, volume is more important than weight. And for others, you know, depending on what kind of application. When you send a rocket, the weight is very important because to satellite 1 kilo costs many millions of dollars. And for like storage, stationary storage, the volume is not so important, and then so you can have actually batteries that are heavy, and it's not a big problem. So anyway, you see here a comparison of different chemistries that are available. This is the lead-acid battery that is used now to start your car every morning. It's here. It's the grandmother of the batteries. It has been invented in the middle of the 19th century by Mr. Planté, and it is still there. And there are a lot of business around it, and probably one of the most successful battery in the world. Lithium lead-acid battery. Nickel cadmium was successful until I would say the late 90s, and now less and less because of the toxicity of cadmium, and it has been replaced by nickel metal hydride. So nickel metal hydride, of those who got their first cell phones in the early 90s, they had a nickel metal hydride heavy battery, but still it's still applied now for some applications, especially in hybrid electric cars. And then all of these are about lithium. So you see, lithium has really changed the picture since 1991, and we're now thinking about, I will make a few comments later about what will be the next generation batteries. And those who are really most attractive and really exciting is how can we use the air, which is free, oxygen in the air to power a battery, and this is called the lithium air, lithium oxygen battery that I will speak a little bit about later. The other very important things about batteries that it's required is power density. So this diagram is called the ragone plot. It allows us actually to compare different batteries according to the energy density and the power density. So here, if for instance I discharge this battery at 1000 watt per kilo, and for this battery I will get something like 120 watt hours. So that actually allows us to compare different chemistries. And of course, basically the R&D efforts are to push this limit to the right and to the left area so as to increase energy and power density. So you see lithium-ion batteries are here, and they are really dominating the ragone plot. The other thing is life. How many cycles can you achieve? And the lithium-ion battery can, in some condition, go between, I would say, 500 sometimes, if they are very cheap or working in very drastic conditions. They can provide only 500 cycles. And under maybe milder condition, or even if you have excellent materials, you can have 3,000 or even 10,000 cycles or even higher. So that's really absolutely incredible. The other very important thing is, I cannot read. 5 minutes? Oh, okay. Well, no problem. The cost of batteries. This is very important. At the beginning, many people said, well, lithium is very nice, but can we afford it? And at the beginning, when Sony was the only producer of lithium-ion batteries in the early 90s, the watt hour was close to $10. And now it is going down to almost 30 cents per watt hour in 2013. That's very good news. That means that lithium-ion batteries now can be more popular, they can be used, and they are cost effective. All right, so there are, in the battery business, there are mainly two major form factor. One is called cylindrical cells, and these ones are used for laptop computers. And you have so-called prismatic cells that are used in cellular phones. And if you increase the size of these, you have the pouch cells, which are almost the same parallelepipedic form. And they are the batteries that are used for electric cars and for energy storage and so on. Okay, a few words about the beyond lithium, the future. So the future in the next, I would say, 10 years would be lithium air. So basically, we are using oxygen to produce lithium oxide or peroxide. And because of the $0 per kilo of air, this battery should be one of the cheapest. And number two, potentially the energy density is at least 5 times what we have today. So I can tell you there is no respectable research center in the world working on batteries that has no activity on lithium air. This is one of the hottest topics today in the area. And who knows, maybe someone will come with very, I would say, breakthrough solution to make this lithium air battery working. We are not there yet. There are many efforts, there are many progress, but we are not there yet. The other system that is now developed is the lithium sulfur. So oxygen and sulfur are in the same column in the periodic table. Sulfur is cheap and environmentally benign, and it can provide very high energy density, and it's also a challenge for scientists and for engineers to provide hundreds or thousands of cycles using this chemistry. I'm myself working on liquid batteries, which means that this battery, you can go to a gas station, empty your anode and cathode, and you can go. You don't need to charge your battery. It's just to replace the anode and the cathode because they are in the liquid state. And we developed this battery, and we have a prototype now in Singapore, and I'm trying to encourage my students to start a company on this. As you said, I like to do this transfer technology between laboratories and start a company and encourage young people to become entrepreneur. And there are also the 3-volt flow redox batteries that are actually another type of chemistry that can apply actually mostly for stationary systems. Okay, I think I will stop here. I have lots of things to say, but anyway, I will have to stop just for sake of respecting the time. Thank you very much. I will take any question from the audience. Thank you very much.